Hi there, everybody. Welcome to another lecture in the electrochemistry series, and what we are going to be focusing on in this lecture is non-standard cell potential. So when we talk about Ecell, we usually have the little knot up at the top of it, which means it's at standard conditions. So standard conditions, when we start talking about cell batteries, involve 25 degrees Celsius, 1 atm, and then any of the aqueous solutions are assumed to be at 1 molarity as far as their concentration for the electrolytes as the electrons get passed back and forth. Okay. Now, certainly that is optimal for doing calculations when we can use that tabulated data. However, it is true that many times we may run into situations where we have non-standard conditions. Specifically, the concentrations is what we're focused on here. So when we take a look at a situation, maybe you have different concentrations other than 1 molarity. How do you solve for Ecell in a situation like that? So we can accomplish this through something known as the Nernst equation. And the Nernst equation is Ecell without the standardization is going to equal the standardized Ecell minus the 0.0257 volts over the moles of electrons being passed in the redox reaction times the natural logarithm of the product quotient. So, if we were to take a look at something like this, let's go back to one of the examples we looked at earlier, which was the zinc and copper example when we were setting up our original galvanic cell. So we had solid zinc, and we had copper 2+ in aqueous conditions, and that went to zinc 2+ in aqueous conditions and copper solid. All right. So if you take a look at this, and I wanted to create Q, now technically since we're talking about equilibrium, we should have an arrow going this way, right? But if I wanted to talk about Q, it's the products over the reactants when I'm working with that. So the way that I could set this up is that I could say that Ecell is going to equal. Now, if you remember, when we originally calculated the Ecell for the zinc copper example, we found that the Ecell at standard was 1.10 volts. So if you don't remember that, go back and watch the video on the galvanic cells where we set up the crude beakers and we talked about the passing of electrons back and forth between the electrodes. Okay, so I'm going to take that minus 0.0257 volts. Right? The number of electrons being passed here would be 2, so zinc loses 2 electrons in this process, copper gains 2 electrons in this process. We can see that from the charges. So I'd put 2 in the denominator for the N, and then it would be the ln of, now I don't have the specific concentrations here, but if they were given to you in a problem, it would be the concentration of zinc 2+, because that's the product, over the concentration of copper 2+. Just like that. All right. So this is a combination of Ecell standard as well as some of the material we were talking about in the thermodynamics and relating it to equilibrium. We put that all together, and then we can look at the concentration of products over reactants in a natural logarithm format. So now let's go ahead and take a look at an example where we are given some values. So right here it says predict whether the following reaction would proceed spontaneously at 25 degrees Celsius. All right, so it's got solid cobalt and iron 2+ going to cobalt 2+ and iron solid. So what we're taking a look at here, you can see the cobalt is being oxidized. It's losing 2 electrons. And in the process, iron 2+ becomes iron solid, so it is gaining 2 electrons through reduction. So in this case, n is going to equal 2, and we'll want to keep that in mind because that's going to go into the Nernst equation when we're working with it. Now we're actually being given some concentration values here. So the cobalt 2 plus is 0.25 molarity, and the iron 2 plus is 0.94 molarity. All right, and keep in mind that when I come back up here, the solid material is not found in any sort of equilibrium concentration, right? So the solids, the liquids, they drop out. So we're not concerned with the actual electrode material as much as we are the concentration of the ions that are in equilibrium through this redox reaction. That's where the molarity is coming in. So what am I going to need? I have to set up Ecell equal to Ecell not, the standard Ecell, with the rest of this equation. So I'm going to need to find the Ecell standard from the charts for this reaction, assuming that it was at standard condition. Then I can solve for the concentrations where it's not at standard condition. Right? So I'm going to need 2 values from my chart. I'm going to need the reduction value for the iron, so that's iron 2 plus and iron, and then I'll obviously also need the one for the cobalt. So that's the E for the CO2 plus CO. All right, so let's go find these values on our chart, which we'll pull up right here. So I need the iron 2 plus and the cobalt 2 plus. So cobalt will be first on the list because alphabetically CO is going to come before Fe. So there's our cobalt. We got to make sure we pick out the right one. Cobalt 2 plus to cobalt solid is negative 0.28. So let's go ahead and mark that down. Negative 0.28. All right, and then for the iron, if we come back, go down, here's Fe. Iron 2 plus to iron solid is going to be a negative 0.44. So here. Okay. So there are the values. Now, remember that the oxidized is going to be the anode and the reduced is going to be the cathode. So the iron is being reduced. Therefore, the iron value is the one that should come first when I'm calculating the Ecell. So it's going to be E naught cell is equal to negative 0.44 volts minus a minus 0.28. So we'll actually add that by combining those. And what I end up with is a standardized cell value at negative 0.16 volts. All right, so now that is just one part of the non-standardized Ecell. We have to have the standardized portion. So I can at this point set it up and say that Ecell for this reaction, non-standardized, is going to equal the standardized Ecell, so negative 0.16 volts, minus 0.0257 volts over N. Now we said that there would be 2 electrons being passed in a situation like this. Natural logarithm of, now I need these concentrations here. So if I take a look at it, okay, it's going to be the cobalt, because that's the product, over the iron, because that's the reactant. So the cobalt is 0.25, that'll be the numerator, and the iron is 0.94, that'll be the denominator. Okay, so 0.25 over 0.94. And all I have to do is plug this into a calculator. So take a second to do that and see what you get. So if you do it all properly, you should have negative 0.14 volts. Now the question was, predict whether the following reaction would proceed spontaneously. Well, we have a negative Ecell here, And that would mean no, we would not expect this reaction to proceed spontaneously, because a negative Ecell means that energy needs to be put into this system in order to get the reverse redox to occur. So it's not going to occur spontaneously as set up, which is probably going to be reflective of the fact that we had a larger negative value acting as the cathode here, in the way that it was set up, right? So that is how we can calculate the Ecell when we are deviating from 1 molarity. We end up using the Nernst equation and setting the standard Ecell equal to this equation with the natural logarithm of the concentrations that are given. So hopefully this makes everything clear regarding how to deal with non-standard Ecell potentials. And then one of the next things that we will move on to is how to actually drive non-spontaneous reactions through certain cells, and that is going to be looking at electrolytic cells instead of galvanic cells. So that will be what we take a look at next.